Raise your hand if you've ever been to a bike sale or a bike auction. Okay, quite a lot of you. So one day, I heard there was this bike sale at Stanford University, where I'm currently doing my PhD in quantum computing. And I heard it would open up at 7 a.m. on a Wednesday. And I was told it was pretty popular, so I should get there early. And I thought to myself, how early should I get there? So I decided I'll get there at 5 a.m. So just before 5 a.m. on Wednesday, I wake up and I'm walking over to this bike sale place. And it's completely dark outside, there's utter silence, and there's no one around. And I'm thinking to myself, I'm crazy, why am I doing this? No one else is gonna be there. And I get to the bike sale place, and there I see 8 other people basically camping out. They have their chairs, their cup of coffee, their scarves, their coats, and some of them had been there since 2 a.m. And I thought, of course, I'm at a university. These are students. They want cheap bikes, including myself. So I actually managed to get an electric bike there for just $35. And I was super happy, and I told my parents, look, I got this electric bike. And as I was riding it, I noticed that it wasn't actually going any faster. And I looked inside, and I noticed the battery was missing. So it was riding just like a normal bike. Now, I tell us this story because this is how we can illustrate how current computers work, known as our classical computers, and how quantum computers work. You could imagine a classical computer, our conventional computers like our laptops, like a normal bike. Especially if you're riding up a hill on a bike, you know it can be a big struggle. And this is just like our current computers. If we give it a difficult problem, it can take us significantly longer to solve a certain problem. Well, quantum computers could change that. A quantum computer is a fundamentally new type of computer that could help us solve certain types of problems significantly faster. You could think of a quantum computer like an electric bike with a battery. It could help us, it has this boost, this extra power that could help us solve certain problems faster. So this brings up a few interesting questions. 1, what problems could we solve faster with a quantum computer? 2, what is the equivalent of the battery in the quantum computer, as in the electric bike? What gives it that boost or that power to solve some problems faster? And 3, what is the current state? When will we have quantum computers, and how can we program on them? So we're going to explore all of these questions in this talk today. And I've summarized these questions in an acronym, MAPS. So we're going to talk about the maps of quantum computing. And so this stands for, first of all, I'm actually going to give you a little bit about my journey. So I was asked to share why I'm talking about quantum computing today. Then we're going to talk about the applications. What could you do faster with a quantum computer? Then we're going to look at the power, what exactly gives it its power. And then we're going to talk about the state of quantum computing, the current state, and where we hope to be in the future. So to start off with my journey, it actually starts 10 years ago in this town called Reading in the UK, and that's where I'm from, and I grew up. And my school got invited to this technology camp at the local Microsoft offices. So this is Reading, not too far from here. And my school got invited to the local Microsoft offices for this technology camp. And there was actually this guy called Chris Bishop, and he was giving a talk on the future of computers. And I remember walking into this room, and he had all of these crazy experiments set up, and I was so fascinated. I thought I wanted to study physics. And you can actually go and watch a similar lecture that he gave online on YouTube called Chris Bishop, The Future of Computers. And so after this, I decided I wanted to study physics. And actually, my parents ended up moving to Copenhagen in Denmark, right here. And so I've actually been visiting my parents for the past few years. I spent high school here, so I'm really glad to be back. And then when it came time to come to college, I decided I wanted to go all the way to the US, and so I actually ended up going to MIT for 2 years, where I studied physics and computer science. And that's where I actually took my first quantum computing course with one of the leaders of quantum computing. He was actually one of the first people to propose how to build a quantum computer. His name is Seth Lloyd. And I was really fascinated, so I ended up doing research with him. And after 2 years at MIT, I actually wanted to go to Harvard, so I spent 2 more years at Harvard University, and that's where I got my bachelor's in physics and computer science. I continued doing quantum computing research, and I hadn't had enough, so I decided to go do my PhD at Stanford, where I'm currently in my 2nd year. And right now, actually, I'm doing an internship at NASA, also in California, in their Quantum Artificial Intelligence Lab. And so you can see that, yeah, I've gone a bit all over the place, but throughout it all, I've really enjoyed doing quantum computing. So that's a bit of my journey, and one of my main areas of research, actually, is the applications. What could we do with a quantum computer? So because a quantum computer is a fundamentally new type of computer, we actually it's not just a faster computer. We can't solve all problems faster. We have to think specifically, what are the problems we could solve faster? So let's take a look at an example. Some researchers have found that if we had the ideal quantum computer, there are actually a whole bunch of problems we could solve faster with it. So let's say I give your computer the number 15, and I ask it, now find me the two numbers you must multiply. Well, of course, that's extremely easy. 5 and 3 give it 15. But what happens if I give your computer the 617-digit number? And now I ask, go find me the two numbers you must multiply. Well, your computer's going to have a hard time doing that, and it might blow up. In fact, we think it could take up to 1 billion years using the best known algorithms to just find what those two numbers would be on our normal computers, or even the world's best supercomputer. So when I, again, refer as classical computer, I'm saying these are the conventional computers. So I'm going to use this terminology from now on. So a classical computer, it could take 1 billion years to find those two numbers. But what about a quantum computer? How long do you think it could take on an ideal one? So we have more polls, but I actually want to see what you guys think. So you can go to polev.com/quantum225, or if you don't have access to the internet, you can text quantum225 to that number, and you can put in your answer, what you think, and we'll see how optimistic or pessimistic you are about quantum computing. Okay, there we go. All right. So you guys are pretty optimistic overall. So let's see what the correct answer is. It's actually 100 seconds. Yeah, so you could, that's crazy, right? Going from 1 billion years to just 100 seconds. And now usually this answer increases once people know the right answer. So how are we able to do this? Well, we can do this using a quantum algorithm called Shor's algorithm. So a quantum algorithm is basically a set of instructions you give to the quantum computer. And there's an MIT professor called Peter Shor who came up with Shor's algorithm. And he showed that it could be significantly faster than the world's best known algorithms if you had a quantum computer to find those two numbers. Now you may think, okay, multiplying two numbers, that's not a very useful problem. Well, it is, if you're familiar with encryption. This is actually what keeps your data internet secure, your bank information, your credit card information. You could essentially think of those two numbers as the key to a lock. As long as no one can figure out what those two numbers are, they cannot have the key to unlock your data, essentially. But if we had a quantum computer, the ideal one, then you can find those two numbers, and therefore you can unlock this lock. And that's why a lot of people are excited about quantum computing, but also worried about it, because this has a lot of implications. Now, what do you actually need to think about this? Well, first of all, I would say it is an important problem we do need to think about, because you can imagine if we need to replace all of our encryption systems to have new encryption systems that could be safe against quantum computers, it could actually maybe take, people think, like 10 years to actually just replace those systems. So we do need to start thinking of new encryption systems that could be safe against quantum computers. And this is an active area of research called post-quantum cryptography. So, but do you need to be worried that the internet is going to blow up tomorrow? No, because as you'll see later in this talk, we're actually pretty far out from building a quantum computer that could actually run this algorithm and therefore break these encryption methods. But this is a problem we should be thinking about now. And there's also this thing called store now, decrypt later, where the idea is you could actually store data now and then have it on your own personal server, let's say, and then decrypt it later when you have a quantum computer, if it's encrypted using the methods that are not safe against quantum computers. So as you can see, it's actually something we do need to think about right now. So another application is in chemistry and physics. So actually, this was one of the first reasons why quantum computing was proposed, because this world out there is made up of particles, atoms, and molecules, and they all follow the laws of quantum physics. And of course, a quantum computer also follows the laws of quantum physics. And so it makes sense. You want to use a quantum system, such as a quantum computer, to simulate a quantum system, which nature is. So with a quantum computer, an ideal one, we could potentially simulate and understand how molecules behave. And you may think, okay, what would that be useful for? Well, that would actually be useful in a lot of different areas. So for example, medicine. In medicine, we create medicine, and it's made up of molecules that interact with other molecules in our bodies. And we want to understand that reaction and what happens. So if we could have a quantum computer that could help us simulate new types of medicines, then maybe we could discover new types of medicines for some diseases. Another application is materials. We want to be able to design new types of materials that can make your laptops better, your phones better. And again, materials are made up of molecules. So if we could understand how they interact and behave, a quantum computer could potentially help us design new types of materials. So you can see we have these two problems here. Basically, finding the prime factors of a really large number and simulating chemistry. And we know actually that quantum computing could solve both of these problems exponentially faster. Now, what do I mean by exponentially faster? So let's say I give you your phone, and now you have to enter your passcode, but there's only one digit you have to enter. Well, that would be extremely useless, because of course, you could just do that in up to 10 tries, you could crack the passcode. But what happens now if I give you 4 digits? Now you'd have to do up to 10,000 tries to figure out what the passcode would be. And now your iPhone actually has 6 digits, and that would take up to 1 million tries. So this is what the problem looks like. As the size of the problem increases only by a small amount, the time to solve it scales exponentially. And there are a lot of problems in the world today that are like this, and why it's hard to solve them on our classical computers. Well, for some of these problems, a quantum computer could do this. It would only scale polynomially, and you can see that it would be especially useful as the size of the problem increases. So I can't be at a machine learning, at a software conference without mentioning machine learning. And actually, there is a field called quantum machine learning. And it may just sound like a lot of buzzwords, but there is some sort of reasoning behind it. Because if you look at machine learning, it's dealing with vectors and matrices in high-dimensional space. And actually, quantum computing under the hood is also a bunch of vectors and matrices in a high-dimensional space. So you could actually naturally map the two together. And we know that we've made progress in artificial intelligence now because of the more powerful computers we have today compared to many years ago. So maybe there could be a new wave of progress in AI if we could use quantum computers to do that. And another problem that you could use quantum computers for is unstructured search. So actually, to illustrate this, I have a bag with 100 balls. So let's say I give you this bag, and I ask you, now go find me the ball number 3. Well, you basically have to pick up one ball at a time, check whether it's the ball number 3, and then continue until you find the number, because there is no structure to these balls. Well, this is how our classical computers work too. If we had 100 balls, on a classical computer, it would take up to 100 tries to find any particular ball. And you could also think of this as, let's say, the entries in an unstructured database. But what about a quantum computer? How long would it take to just find the ball number 3? Well, it could take actually just 8 tries, even when there's no structure. And it's not an exponential speedup. Not all quantum computing algorithms have to be an exponential speedup. It's actually a quadratic speedup. So in the classical case, we'd have to do up to n tries. We can generalize this. But in the quantum case, you can do up to square root of n tries for any unstructured search problem. And how are we able to do this? Again, there's another quantum algorithm called Grover's algorithm. So a guy called Grover created this algorithm. And later in this talk, we can see how you can actually program this algorithm on a quantum computer. So here you can see we've covered these 4 applications. factoring, simulations, machine learning, and search. And you can see that these problems are so broad or general that they could be applied to a lot of different industries. For example, artificial intelligence, medicine, materials, and maybe more speculative ones such as finance, space, and logistics. To summarize, with quantum computers, we could solve the unsolved problems. We could tap into problems we've never been able to solve before. Now again, this is with the ideal quantum computer, so these are all potential future applications. Now you may be curious, okay, how is it able to do this? So now we're going to look into the power of quantum computing, and we're going to have a little teaser for how it works. I can't go into all of how it works because there's a lot to cover, but we're going to look at one particular case. So the power is basically quantum physics. So as I mentioned, quantum physics just describes how the world works at the most basic level, at the level of atoms and subatomic particles such as electrons. And so a quantum computer basically harnesses the quantum physics laws to build computers. And so in particular, we're going to look at one principle of quantum physics, which is called superposition. So to illustrate this, let's recall how our normal computers work. We have bits, zeros and ones, and anything can be processed or stored as a sequence of bits. Well, it's the same in a quantum computer, but there is a big difference. So let's say we have a classical bit. And to illustrate this, I have a donut. So let's say the frosted side is equivalent to 1, and the plain side is equivalent to 0. So this is a classical bit. And then basically you go sequence 1 zeros, 1 zeros. Now, what about a quantum bit? Well, a quantum bit can actually be 1, it can be 0, but it can also be a superposition of 0 and 1. And I think of this like a spinning donut. When it's spinning, and I ask you, is it 0 or is it 1? You'd say, well, it's a combination of both. And this is a quantum bit, or also known as a qubit. So, what is the power of this superposition? Well, let's say I give you a donut box, and inside you open up the box, and there you see 2 donuts. You'd either see, if you had 2 classical donut boxes, you'd either see 0, 0, 0, 1, 1, 0, or you'd see 1, 1. But what happens if I give you a quantum donut box? Now, you see them spinning inside, and I ask you, which combinations do you see? Well, you kind of see all of them at the same time. So as you can see, we're now in a superposition of all of these combinations. And so the power here is that you can be in multiple combinations at the same time. So when you're doing the processing, you're actually processing on all of the combinations instead of just one at a time. Now, I have another question for you, and you may have to do a little bit of mathematics, but how many combinations would there be if you had 300 qubits in superposition? So you can go to, again, the poll, pollev.com/quantum225, and we'll see what you guys think. Okay, interesting. So it looks like you guys went with the largest number, so now you're optimistic. But actually the answer is, okay, now it's getting more correct, 10 to the power of 90. That's an insane number. That's 1 with 90 zeros after it. And actually, that's so insane, that's more than the number of atoms there are in the observable universe. So why was it 10 to the power of 90? Well, anytime you have n qubits, or quantum bits, you can basically represent 2 to the power of n classical bits. So in this case, we had 300 qubits in superposition, so you'd have 2 to the power of 300, which is roughly 10 to the power of 90. And so you can see the power in quantum computing just from this small example. And there are other quantum effects that you may have heard, such as entanglement and interference, but these other quantum effects are similar, and in combination with all of them, that is how we can get the power in quantum computing. So you may ask, okay, how exactly do we then use superposition to actually make a computer and operate in a computer? How does it operate? Well, a quantum computer operates in a similar way to classical computers, although there are some big differences. So let's look at how a classical computer operates. You have logic gates. So let's say you have the bit 0, you put it through a NOT gate, and you end up getting 1. Or if you put 1, you'd get 0. So this is how our computers, very simplified, work. You have logic gates, then you can build up basic modules like addition, and then you can build chips based on these modules, and then circuit, and you have your computer. Well, quantum computers work in a similar way. Instead of logic gates, we have quantum gates. So what is the difference? Well, we can actually have the equivalent of a NOT gate. So let's say we have something called the bit flip gate, and it's also called the X gate. So if we have our classical bit or our quantum bit, we put it through the X gate, and it ends up flipping it to the other side. And if we had 0, it would go to 1. So this is just classical, right? Because it's just flipping the bits. But now we have something more interesting. We have something called the Hadamard gate, which can actually make our qubit go into superposition. So now it goes through, let's say, a 0, and it ends up coming out in superposition. So we have also other types of gates that can do other effects, like there's a gate for entanglement, for example. But you can see then when we build multiple of these quantum gates together, we actually build a quantum circuit. And so you can execute a quantum algorithm by using these quantum gates. And your goal of the algorithm is to use quantum effects, such as superposition, in special ways to solve a problem. So now we can look at a very concrete example. Remember Grover's search? And this was the one where we want to find one ball in a bag of balls. So to simplify the problem, let's say we only have 4 balls, and I want to find the ball number 3 again. So we're going to see how you can actually implement this algorithm using the quantum gates. So classically, it would take up to 4 tries, but on a quantum computer, it would only take 1 try to find the ball number 3. So again, because quantum computers also work with bits, you need to convert the number to bits. So we're converting number 3 to bits 1, 1. And so our goal of the algorithm is to find the bits 1, 1. So this is actually the quantum circuit you would use for Grover's search. And here I'm just going to highlight the gates we've already seen. So you can see that you've actually seen the majority of the gates. And each line corresponds to 1 qubit. So we have the first qubit at the top and the second qubit at the bottom. And you can see that we're applying these quantum gates to the qubits. So they basically go through, and at the end, we'll end up getting the bits 1, 1. And these other quantum gates, you see, are the ones that do sort of these other special effects, for special quantum effects. So you can see that you can actually implement any algorithm using these quantum gates. So now, how would you actually program a quantum computer to do that? Well, you can. So you can program a quantum computer by using these quantum gates. And so let's take a look at a very simple example. So here is a visual example, and this is called the IBM Q experience. So you can look this on Google, and it allows you to basically drag and drop gates so that you can implement a quantum algorithm. So here in this case, we have 5 lines, and they actually correspond to 5 qubits. So in this case, I'm only going to use the top line because we're only using 1 qubit. But in this video, you can see this is the Hadamard gate we saw. I'm just dragging the gate, I'm dragging another one, and then you can click run, and it will actually then run on a real quantum computer. So you can see it says that it's been sent to this IBM Q16 Melbourne, which is their quantum computer. And this is a cool visual way to actually run algorithms on a quantum computer. And anyone can go and do this online for free. Now, if you want to do something more complicated, it's a bit hard to drag and drop gates. So you can actually write some code to program a quantum computer. So here's a quantum computing API for Java, and it's called Strange. So here's some simple code to show you how easy it is to actually code on a quantum computer. So in this case, I'm basically just creating the method quantum circuit. So, and this is just in Java using this API. Now I'm creating the simulator. So I want to clarify what I mean by simulator. So you can actually simulate what a quantum computer does. Because as I mentioned, quantum computing is just matrices and vectors. So in fact, each quantum gate corresponds to a matrix, and the qubit corresponds to a vector. So when you simulate it, you're actually just multiplying these matrices. Then you may ask, well, what's the point of the quantum computer if we could just simulate it? Well, these matrices get really large, and it gets really inefficient to actually do these calculations. And in fact, it's exponentially slower to simulate a quantum computer on a classical computer. But if you're only working with a few qubits, it's fine to simulate it. But once the number of qubits gets larger, then you can no longer simulate it. So here we're just going to simulate it, but there are also APIs where you can run it on a real quantum computer. As the one I showed you before, IBM has one where you could actually run it on the real quantum computer device. So in this case, I'm creating a new program, and one specifies the number of qubits. So I'm creating a program with 1 qubit, and then we're adding steps. So these are basically just the sequence of steps you're going to take in your quantum algorithm. And to this step, we're going to add the gate, the Hadamard gate. Remember, this is the one that puts the qubit into superposition. And we're applying it to 0. So we're applying it to the 0th qubit. Then after that, we're going to add the step to the program. And then you can basically run this program on the simulator. And here you're actually running code for a quantum computer. So as you can see, it's fairly simple. And there are also other APIs in Python, for example, and other languages that you can look up online. So you may ask, okay, if we're actually running it on a real quantum computer, what is the quantum computer made of? How do we actually build a quantum computer? Well, how do we build our normal computers? Let's start from there. So we have transistors, as you may know, and basically we need something that represents a bit, right? We need something that can be 0, we need something that can be 1, and transistors basically block and allow the flow of electrons to act as 0 and 1. But it didn't actually used to always be that way. People used to use vacuum tubes in the old days to build computers. But transistors ended up being more scalable, much more easier to use, which is why we use them today. And transistors have taken off, as you know. But the reason I tell this is because it's also similar in quantum computing. There's actually many different ways to build a quantum computer right now. And if you want to build a quantum computer, you need something that can be a qubit. So it needs to act as a 0, it needs to act as a 1, but it also needs to be in superposition. It also needs to have other quantum effects. So there are actually different ways to build a quantum computer. So some ways include superconductors. We can also use trapped ions in a vacuum. So ions are atoms with a net electric charge, and we confine it into a vacuum, into a space. We can use photons, which is light. And you can even use diamonds. So as you can see, there's many ways to build a quantum computer. And it's really an exciting time because we're not really quite sure which is the best way to build one. I would say that superconductors are the most popular one. As we'll see, Google and IBM, this is the method they're using to build a quantum computer. But we're not quite sure if that is going to be the winner, if that's going to be the equivalent of the transistor. Maybe there'll be a new technology that will outperform all of these. But, and I actually have a friend who's working on quantum computing at Stanford, and he's working on diamonds one, and they just manufacture diamonds, and he actually said, yeah, if you just want a diamond, let me know. I was like, yes, please. Very casually said that. So as you can see, there's many different cool ways to build a quantum computer. Now, you may be asking, well, why haven't we built a really large quantum computer? We have built quantum computers, but they're still very limited. What are the challenges? Well, one of the biggest challenges is we can illustrate through this spinning donut. So the spinning represents superposition. But in real life, you see it eventually stops spinning. And it's actually similar with quantum computers, with qubits. If it's in superposition, it eventually loses its superposition. And so it's hard to do long computations because if it loses it, over time. And you can imagine if you had many qubits, it's even harder to control all of them because they all eventually lose their superposition at different times. And so it's very hard to control a quantum system. And in addition, if this is a qubit, and let's say my fist is an atom or an air particle, you can see that it can just interact it, and it bumps into it, and it just loses it. So that's why we need qubits to be isolated, because if it's not, it's basically interacting with all the other air particles or photons from light. And so when we build a quantum computer, it's really important we need to isolate the quantum computer. And there are many different ways to do this. So actually, one way is by using a vacuum. So here I actually have an experiment. You'd probably be wondering what this is. But vacuum technology is important in a lot of different ways to build a quantum computer. Because as you know, a vacuum, you're basically pulling out the air, so then there are no more air particles. And this is used in superconducting quantum computing. It's used in trapped ions. And so a vacuum technology is really important. And I happen to have one at home, so I wanted to show you some cool experiments you could do with a vacuum. So let's actually take a look what we can do. So I have a question for you before we start that. So basically, I have some water in this vacuum, and my question to you is, what do you think will happen to this water initially when I put it in this vacuum? So maybe you know a bit of the physics, or maybe not, so you can try and do this. Okay, cool. So let's see, most of you think it will boil, so let's take a look. So I actually have, I have the experiment here. And let's switch, there we go. All right, so here you can see I have this little setup. Ooh, and that disappeared. Oh, okay. Okay, let's set it up again. Here we go. So here I have a vacuum pump, and this is basically going to pump out the air through this tube. Here I have a vacuum chamber. Here this tells us the pressure. Right here, this is the pressure. Here I have the water, and I have a thermometer to look at actually what the temperature is of the water. And as you can see at the moment, it's about 23 degrees Celsius, if you can see it. So I'm going to switch this on, and we're going to see what will happen. So as you can see, the pressure is decreasing, so I'm pumping out the air. And then eventually we'll go lower. And there's some vibration from the vacuum pump. So we may have to wait a little bit. Now you may be able to see, okay, there we go. Now you can see the water is actually boiling. And if you look at the temperature, the water is actually only at 22 degrees Celsius. So basically what's happening is when you're pulling out the air, the pressure is decreasing. And when the pressure is decreasing, you actually lower the boiling point of water. So now the boiling point of water is much lower, and we're boiling water at only 20 degrees Celsius. And you can see the temperature is actually decreasing because the energy is escaping as it's boiling. So that's a vacuum. And I thought it was a little experiment to show you guys. So let's go back to... Okay. But the reason I show you this is, because a vacuum is a very important piece of technology for quantum computers. And you may have heard some people have proposed building a quantum computer in space. And that's because space is a vacuum, so it would make it a lot easier so we don't have to have all of this equipment to just control a quantum computer. But I think there's more problems with building a quantum computer in space than, than having the vacuum equipment. So maybe that's not ideal. But okay, so let's see. So as I mentioned, we've actually built quantum computers. So here's a picture from IBM, and this is their quantum computer. And it's funny because all of this equipment you see is actually just to control the quantum computer, but the actual chip itself is like this small. It's really small, and it's at the bottom of this sort of chandelier-looking thing. So now we're going to go in, what is the state of quantum computing? So how far have we gone? How big of a quantum computer have we built? So I have another question for you. How many physical quantum bits do you think we've actually built now in a quantum computer? So you can go to this poll, Again, polev.com/quantum225. And I want to see how big of a quantum computer you think we've already built. Okay, so most of you say 50 to 100, and actually that's right. So currently we have about, the largest quantum computer that we know is public is about 53 qubits. So this is our current state on this graph. We're at 53 qubits. Now, what is the goal? Where do we want to be with quantum computers? Well, you may have heard that there's this new exciting announcement. So there's been a lot of news, and I'm curious, raise your hands up if you've heard of this quantum supremacy stuff. Okay, quite a lot of you, yeah. So this is actually a really exciting time to now talk about quantum computing, because Google and NASA achieved this thing called quantum supremacy. So what exactly is it? Well, if we go back to my introduction when I talked about the bikes, you have the classical bike, sort of a normal bike, and an electric bike. You can think of quantum supremacy as a race between the quantum computer and the world's best classical computer, a supercomputer. And basically, we're giving these bikes a particular path, and we say race, and let's see how long it takes you to get to your final destination. So we gave the supercomputer and a quantum computer the same problem, and we say go and see how long it takes. So Google said they were able to run this problem in 200 seconds on their quantum computer, whereas it would take the world's best supercomputer 10,000 years. They claim it would take 10,000 years to actually solve this problem. And so this is what the quantum supremacy thing is about. And actually, I was at a tech conference recently, about a week ago, and the presenter of the conference, he was talking about quantum supremacy, and he was like, go ask Jessica what that means. So then I had a bunch of people come up to me afterwards, and they asked me a bunch of questions, but I was really shocked to find out what the most common question was. It was actually, is it real? So I see there's a lot of pessimism or skepticism, let's say. But yes, actually it is real, and I understand why, because there's been a lot of news from many other companies, let's say, talking about quantum supremacy. But it is real. I've actually gone and visited Google's quantum computer, and it's really cool to go see. It's like you're walking into the future. But a few months ago, I gave this talk, and I actually had this slide. It was like the current state was everything you can do on a quantum computer, you can do on a classical computer. So up until the quantum supremacy experiment, this was true, because you could basically simulate a quantum computer, right? But now, with the quantum supremacy experiment, this is in the past. And now there's one exception to the problem. One exception is that the quantum supremacy experiment you cannot do on the world's best classical computer. So we can see that we have we've gone from 0 to 1 in the sense that we've gone from 0 problems that we can solve faster to 1 problem we can solve faster. Now you may think, okay, one problem, here's the one problem with the 53 qubits. That's not very useful. But I would say it's a big achievement, because before this, we actually didn't know whether you could do anything faster on a quantum computer, because you could always simulate the quantum computer. So this quantum supremacy experiment is really exciting, and I think a really big confidence boost in the field of quantum computing to show that it's possible with our current quantum computers that we could do something the world's best supercomputer cannot do. But as you can see, we're quite far away from sort of many useful problems. And actually, our ultimate goal in quantum computing is to get to this state. It's to get to a large-scale quantum computer. And this is one with millions of qubits. And we know, this is when I talked about the applications, this could solve many useful problems a lot faster. So you can see there's a big gap in between, and we have some way to go. And Shor's algorithm, which is the one that could break encryption, that's the one that would need millions of qubits. So right now, there's this sort of large unknown. We're not really sure what's going to happen in between. So maybe one of the worst case scenarios is we don't really make much progress, and really we only start getting more useful problems when we have a really large quantum computer with millions of qubits. So this would be like, okay situation, not that great, because then we'd have to wait many more years before we could do anything useful with a quantum computer. Or maybe something more exciting would be that now we start to find more problems that we could solve with the quantum computer faster than the supercomputer. And it turns out maybe actually we don't need a large-scale quantum computer. We could do it with the existing ones we have now. Or maybe it's a bit more scattered like this. We're not really sure. Maybe we solve a problem and we're like, oh yeah, it's faster, and then we realize, no, it's not faster. And it's sort of back and forth between the supercomputer and a quantum computer. So this is the large unknown. But my thesis in this talk today is actually this is an opportunity for quantum developers. Because if you think about it, the hardware, it's kind of obvious what we need to do. We need to make better hardware. But in the case of solving problems in specific applications, this is actually where developers need to come in. They need to figure out how can we take advantage of the quantum computer and how can we find new applications for it. Because as I mentioned, it works in a completely different way. So we have to think, and people need to put their minds to it to actually find these problems. So we need to develop the next developers for quantum computing. And one of the amazing things right now is that anyone has access to the quantum hardware. So, back when computers were first built, only if you really had a computer could you do something with it. But the amazing thing about quantum computing now, and because of the age we're in, is that you can actually access a quantum computer through the cloud. So you don't need to have a quantum computer in your room to code on it. You can just do this through the cloud. And that's why it's, I think, a great opportunity and why it's sort of more open to more people right now, because there's not a higher barrier to entry, except you have to learn quantum physics. But now anyone has access to the quantum hardware. So a lot of companies are working on this. I mentioned IBM, Google, Microsoft, and they all actually have their own APIs. So you can look up IBM Quantum Computing API. Google has their own one called Circ, and Microsoft has one called Q#. So universities are also working on quantum computing. We have, MIT, University of Copenhagen, right here, Oxford and Waterloo in Canada. And there are actually a bunch of startups in quantum computing. So we have Rigetti, which is based in Berkeley, Zapata in Boston. So I actually have another question for you. How many startups do you think are working on quantum computing around the world? So let's see what you guys think. It looks like the Wi-Fi is down. So anyway, but the answer is more than 100 startups. So there's actually more than 100 startups working in quantum computing around the world. And it's really cool. So there's this website called Quantum Computing Report. And you can actually go see a list of the private companies. And I think it's pretty amazing and up to date how they keep it, because I actually advised some venture capital firms on investments in quantum computing startups. And I remember I had a meeting with one quantum computing startup and with this venture capital firm, and we were assessing it. And then a few weeks later, I actually saw this startup on this website, and I was like, oh, that was quick. So they really keep it up to date, which is great. So there are a lot of startups working on quantum computing around the world. So now that brings the question, what needs to be done in the field of quantum computing? How can we get to all of those amazing applications I mentioned earlier on? Well, I came up with another acronym, MATHS. So first of all, we need to hit another milestone. So we've hit the milestone of quantum supremacy, but now there's the next milestone, is quantum advantage. So this is the idea that the hardware could solve a useful problem significantly faster than the world's best classical computers. Because I don't know if you read about the quantum supremacy experiment, but it's kind of, people think it might be a useless problem. So we talked about the quantum circuits, and basically the idea is you take a random quantum circuit and then you run this on a classical computer and a quantum computer. So a random quantum circuit may not be actually that useful. But so that's why the next step is actually let's solve a useful problem and maybe a potentially commercially useful problem. So after that, we need to continue to develop applications. As I mentioned, this is an opportunity for quantum developers where you can create algorithms for useful applications for existing quantum computers, because we need to put our minds to that as a quantum computer works completely differently. Then there's a lot of theory that could be done. There's a lot of theoretical computer scientists that are looking at what problems are hard to do classically but easy to do quantumly. So more theory needs to be developed. And of course, the hardware needs to keep improving. We need to increase the number of qubits. And I should note that it's not just the number of qubits that matter, but also the quality of the qubits. Because if you remember, we have our superposition with this spinning donut. Eventually, it stops spinning. And so this is sort of the quality of the qubit. How long can it be in superposition for? How long can it keep spinning for? So this is what we need to do, is increase the quality of the qubits as well as the number, and also reduce the error that there are. And finally, we need to shift our mindset. So shift our mindset from the classical realm to the quantum realm. And there's a lot of interesting things that have been done around this. There are some quantum games, such as quantum chess. There are a bunch of hackathons that you can go attend. IBM has these great hackathons in Europe, in Asia, in Africa, in North America, where they invite quantum developers to come and actually hack on their quantum computers. And I've been to one of them, and it's really fun. But also we need to sort of think, how can we think in the quantum sense? And actually Peter Shor, who created Shor's algorithm, the one that could break encryption, he actually wrote a paper, and he said, why haven't more quantum algorithms being designed? And he suggested, well, computer scientists think classically. We don't think in the quantum sense. So how can we think more quantum? So as I've showed you, we could solve some problems significantly faster with a quantum computer, which could help us understand nature more accurately. And that could advance medicine and maybe artificial intelligence. I would say there are two future states of the universe. One where we have the large-scale quantum computer with millions of qubits, and one where maybe we don't have a large-scale quantum computer because maybe it's impossible to build, or there's some big engineering challenge we can never find. Well, right now, we're in a superposition of both. Who knows what's going to happen in the future? But as a quantum developer and as researchers, our goal is basically to break that superposition paradoxically, so that one day we'll have a quantum future. Thank you.